first one, look at function y equals 2x. Actually, sorry, f of x equals 2x plus 1. The second one, y equal f of x equals g of x. Those are all sorts of other things. G of x equals x squared plus 2x. Third one's going to be a graph like this. So here's our y equals f of x. Not f of x, it's given this name called k of x. Something like that. Another graph for number 4. Y equals h of x. And then finally, fifth one, we'll look at s of x equals square root of x. Okay, so here are 5 functions, and what I want to know is which of these functions have inverses. I'm not asking you to find the inverses right now. I just want you to tell me whether or not they have an inverse. I may ask you for a justification, so if you're ready to do that. Okay. All right, first one, yes or no? Okay. You say yes. Can you justify why it has an inverse?
It's linear.
It's a linear function. If you were to graph it, you'll see it does in fact pass the horizontal line test. So for the first one, yes. Justification, the simple justification is linear functions have inverses. And put a little star there for a moment because, well, I'll get to it in a second. All right, so 1 is yes. What about number 2? Okay, why?
It has an even exponent.
Okay, so people oftentimes when they see functions like this, they say, no, it's a parabola. So yes, it is a parabola. No, it doesn't have an inverse. A good justification on this one would be either to produce the picture or to give me a y value and 2 different x values that go to that y value. In this case, what you could see is that y equals 0 comes from, what are 2 x values that both get sent to 0? I'll give you a hint, one of them is 0. What's the other one? The radicals. What's that?
-2.
-2 is the other one. Okay. So this is a good justification here. We've demonstrated that it's not 1-to-1 because this single output came from these 2 different input values. Okay. So that's one way we can. Right. What about the third one here, number 3? Based on the picture that you're given, what do you think? Okay. This one should have an inverse, provided I didn't draw out any weirdness. This one should be a function with an inverse. Again, this instance it passes horizontal line test. But number 4 here. Does everyone believe number 4 has an inverse? I hope you do. Number 4, yes, it also passes the horizontal line test. If you're interested, this type of graph shows up from functions that look something like 1 over, let's see, this would be something like that. And this is an example of the graph of a function like 1 over x plus 1. And yes, it does have an inverse. What about number 5 here? Y equals the square, s of x equals the square root of x. What do you think? Yes, no?
Yes.
Yes. This one should have an inverse. It should be a yes answer here. And there's a couple of different things you can do with this function to see that. One thing about this function, if you were to graph this y equals the square root of x, this function looks like this. Okay, looks like a little parabola on its side with just one of the two pieces here. Now, another thing that you can use to justify this is notice this function is increasing everywhere, right? It increases from start to finish. It's always getting bigger and bigger. Okay? Functions which are always increasing and functions which are always decreasing are automatically one-to-one. Okay? So if you have an increasing function, it's one-to-one. Increasing everywhere. So, same thing with decreasing functions. If a function is decreasing everywhere, it's also one-to-one, and so it will have an increase. All right. So, identifying whether a function has an inverse is a good tool to have. Now, we haven't yet talked about how to find those inverses, and we'll get to that in a few minutes, but sometimes it's not easy to find the inverse of a function. Okay? And just because a function has an inverse doesn't mean that you can write down a formula for it. There are lots of functions out there which have inverses, but for which the formulas for those are not able to be written down. All right, so next I want to talk about involving these inverse functions is sort of how do these inverse functions relate back to their original functions? And there's a couple of different properties we're going to look at in that respect. The first thing we're going to look at is we're going to look at the relationship between the domain and range of a function and its inverse. And we're going to motivate this with a picture of a function, and, well, we might as well just use that square root function for now. Here's our 1, x, y. All right, now, if I look at a point on my square root function, okay, this point right here came from that x value, and it has that particular y value. Okay, so f of x equals square root of x. Okay. Now, remember the inverse function sort of undoes the original. So f the inverse, which we'll call g of y, gives us out x values, right? The inverse function is going to take the y values for our inputs, and it's going to spit out x values. All right? So, if I ask you to identify the domain of the inverse function, okay? So, I ask you for the domain of g of y. Now, I have an example up here on the board, and an example is useful for illustrating a point, but think about this sort of a little bit more abstract. Don't think of this particular function, and don't think of trying to find the domain of this particular function. Think about what the domain of any inverse will be in relationship to the original function. Okay? We look at this one. Okay, we're thinking about what inputs, what am I sticking in to the g function? What values go into that g function? In this particular example, we're looking at positive values. Positive values do in fact go in for the g of y here. Okay? In fact, if I want to look at this, I can say that the domain of g of y, domain here, is all positive or non-negative real numbers. Okay? That's the domain in this particular case. Now let's think that we have an arbitrary function. Okay? Here's a specific example. Let's go to a, say, more complex one, like do this. All right, let's see. And actually, there's something like this. Okay. All right. Now, this picture here. Again, if you look, this is a graph of a function, more or less, and this function is invertible. Just like over there, if I pick a specific point, so this is y equals f of x, and I'm looking at g of y equals x. This is the inverse again. What values do I plug into the g of y function? What values? Don't think of them in terms of positive reals or negative reals or every number except 0. Think about what values go into that function. What am I sticking into the inverse? What am I sticking in?
The output of the original function.
Right. I'm sticking in the outputs of my original function, right? Because that's what the inverse does. It undoes the original function. So it takes the inputs of the original function and undoes whatever the original function did. So when I'm talking about the domain of the inverse function, the domain of g of y equals the outputs, or the range, of f of x. That's the relationship we get between the domain of an inverse function and the range of the original function. Okay? All right. So then, if I ask about the range of g of y, what output values do I get from the inverse function? What are the outputs of the inverse function? They're exactly the inputs of the original function. So the range of g of y is the domain of our f of x function. Okay? This relationship right here is oftentimes useful for finding the domain or the range of the opposite or the inverse function that you're working on. Okay? For example, this this top one here. We spoke earlier in the week about how it's oftentimes difficult to find the range of a function. It can be difficult to find the range of a function. But if that function has an inverse, and I can write down a formula for that inverse function, then I can utilize the rules of domain to figure out what the output values of f are. Okay. So this is one tool that we can use to identify the range of a function if that function has an inverse, and if I can write down a function, an equation. Okay. All right, so let's take a look at an example or two of this. All right. So we'll start with the square root function f of x equals the square root of x. I want to do two things here. I want to find the inverse. I want to find the domain and range of the inverse. And just for giggles, let's go ahead and graph the two. Start with this one, and we will work forward. Okay. Inverse function. What's the inverse of this function look like? What does it have to do? Okay. If we think about what this function is doing, this function takes the square root of a value. So it takes a input and it figures out how much I need to decrease it by in order so its value is square rooted. Okay? So the inverse function, we'll call g of y for a moment. In this case, it'll look like y squared. That's what the inverse